Hey everybody, welcome to our video on rotational motion. This is going to be a 3-video series. We're going to be rotational motion part 1, part 2, part 3. Anyway, let's get right into it. All right, so this is a math that you have frankly seen before already. I'm just going to go through it really quickly here just so you can have it in your notes and you can always review. So theta, if of a circle, right? What would our theta be? Theta would be our angular position, all right? In rotational motion, we talk about the position relative to how the object rotates, and where the object is at the time is angular position. S there is basically just the arc length, really, or if you like, distance traveled. All right, and put this nicely, sorry. I'm gonna just say distance traveled. It's normally a surface area. And R is the radius from the center. All right, so we must know how to mathematically show a full rotation from a circle in radians, in the unit of radians, all right? Like, what does that look like in radians? Well, we can derive it, and we've derived it before. So I can say my delta theta, which is going to be my angular displacement, by the way. Angular displacement, my delta theta, going to be equal to delta S over R. All right, then I can ask myself, what's the distance traveled around a full circle? What's the surface area of that circle? I'll say delta theta is going to be equal to 2 pi r. And then from there, I have to divide by r because the r is over there. Then I can the arrows cancel here. And I see that the total displacement for a full circle, is really 2 pi radians, 2 pi rad. That's 2 pi in radians, all right? We're dealing with radians. So this is basically an angle. And what's this angle called, really? What's this angle? What's the angle? The angle is 360 degrees. So I might also give you a conversion factor to get between radians and degrees. So we're going to have 2 pi radians equals 360 degrees. All right. If I divide by 2 pi, I see that 1 radian is going to be equal to 360 degrees over 2 pi, which is, I think, approximately 57 degrees or so. I can check that. Yeah, approximately 57 degrees. So 1 radian is equal to approximately 57 degrees. So yeah, that's how you convert from radians to degrees, if you want to understand degrees. Now we can talk about angular velocity, all right? You know, linear velocity is displacement over time. Angular velocity is the same thing. Omega is going to be delta theta over delta t, all right? The angular displacement over the total time it's taken, right? And there's another way we can write this. Right? Omega, if I calculate omega using the radius and the total period, I need to cover for one full revolution, one full lap around the circle. I can say my angular displacement will be 2 pi r, and my time will be the period. All right. So here I'm saying delta theta is equal to 2 pi r, and the delta t is going to be 1 period. So it's the rotation. It's the one full rotation over the time it takes to complete one full rotation. And let me help you visualize the angular velocity, yeah? So here, an object that's rotating has both an angular velocity and a linear velocity, right? So imagine this is my object rotating. My linear velocity is what helps make it move, right? So my linear velocity will just be this the velocity that makes it move in a straight line. But now my angular velocity really is how fast is the object spinning, all right? How fast is the object spinning, all right? And this is how I want you to think about it. It's making the object spin. That's what angular velocity is, all right? How fast is the object spinning? So anyway, let's get into the relationship between the linear velocity and the angular velocity, right? So we know linear velocity is just delta x over delta t. That's the distance, our displacement. Here in angles, we say displacement is delta s. It's going to be delta s over, delta s over delta t. And then we know what delta s is from the full, from right here, from here. We can solve for delta s. I can see that delta s is equal to r theta. I'm cross multiplying here. Then I can plug the r theta back in. I'll say v is equal to r theta over delta t. Yeah, r delta theta over delta t, sorry. And I can say v is equal to r omega. That's because you see this over here, delta theta over delta t, delta theta over delta t, that's omega. And there's our relationship between the linear velocity and the angular velocity, all right? If we can also, this is just the same formula equivalent, depending on what you want to find in your particular question. So this is the stuff we've talked about a lot. I hope this explanation made sense. So rigid bodies. So in this section, we'll be working with rigid bodies. Sorry. No, it's correct. With rigid bodies. Up to this point, we mainly dealt with particles. Why? Well, because they have no shape or size and only a mass. So the math was easy, all right? So the math was easy. So this makes, it made mechanics a lot easier for us, all right? Now, when talking about rotational mechanics, we're gonna deal with rigid bodies, and this is where we actually consider an object's shape and size in our dynamic equations. So, a rigid body is defined as an object that has a shape and size that does not deform when it moves, all right? So, and just here to highlight the key difference, but a particle doesn't have a shape at all. It's just a point, all right? A particle is just a point mass, all right? But now a rigid body has a shape, it has a mass, and those shapes and masses stay stable as they move. So yeah, here's just a quick description, a quick side-by-side description of particles and rigid bodies. So a particle has a shape, a size, often referred to as a point mass. It can move translationally. That just means it can move linearly with linear velocity. It has no angular velocity. However, if you tie a particle or put a particle in a gravitational field, it will rotate. It will go in a circle and experience angular velocity, but itself won't have intrinsic angular velocity, and it cannot rotate. So, yeah, but a rigid body has shape, the size, all right? It can move translationally. All right, it has all the linear kinematics applying to it, the linear velocity, linear acceleration. It can move rotationally. All right, it can rotate. That's what's good. And a combination of both. All right, so these guys can like, do you remember the wheel? I was able to rotate the wheel and move it in the linear direction. So that's what makes rigid body is so great. So yeah, let's see. It has an angular velocity, acceleration, and time. Oh, acceleration, and yeah. Anyway, I'll just say it has an angular velocity and acceleration. Yeah, yeah. However, the great thing is that at all points of the rigid body, it will experience the same acceleration everywhere. Same acceleration. So the same acceleration, the same velocity, and the same angular displacement, all right? So same acceleration, same velocity, and same displacement. And this is all angular, by the way, all right? And yeah, if you don't understand this, please come to my Highland Advocate hours. So let's talk about angular acceleration. What happens when an object, what happens when angular acceleration is happening? So when angular acceleration is happening, angular velocity is changing. All right? So because of this, because the angular velocity is changing, right, the object does not experience uniform circular motion. Do you remember how we define uniform circular motion? The velocity had to be constant. I was only accelerating because it was changing direction. But now we are changing direction quite all right, but we are also changing our velocity. So both of them are accelerations, but the other one, angular acceleration, is also rotating tangentially, so to say. So yeah, and we know it by alpha. The formula for angular acceleration is just a change in angular velocity over time. Something I believe we're comfortable with. And like with this bike example, just think about, remember my example of me swinging the tire? Think about me hitting the tire, making the tire get faster, such that here at t equals 1, I give it an angular velocity, and at tf, or is ti and tf. So at ti, I give it an initial angular velocity. At tf, I change it by hitting it, all right? So at each point I hit the wheel, and it hence it's going faster and faster in the horizontal direction. So that's really the logic of angular velocity. So now, now the sign of angular acceleration. How do we think about it? Like, when is angular acceleration positive? When is it negative or so? Well, all right, a good rule to follow is angular velocity, angular acceleration, apologies. Angular acceleration is in the same direction when the angular velocity is speeding up. All right? And opposite the, I didn't write velocity there. And opposite the angular velocity when it is slowing down. All right, and a lot of these rules are similar to the kinematic rules. This is how linear velocity works as well. So let's look at this picture here I got from your textbook really quick. So we see we're rotating counterclockwise and we're speeding up. So if you remember very well, when we have our circle, and I have my horizontal line, and I have theta. Positive theta is measured counterclockwise. So if I'm rotating counterclockwise and speeding up, so my theta is positive, and I'm speeding up, so that means that the slope of my velocity time graph is going to be positive. So I definitely, so that's what I mean. I know A is definitely positive here. Rotating clockwise and slowing down. Well, how we can look at this one is if I'm rotating clockwise, right? That means theta is negative, but I'm slowing down. So it means I'm getting less negative. So if I have a velocity time graph, right, I am going from the negative side to the positive side, all right? And because of that, because I'm getting less negative so because I'm getting less negative, acceleration here is going to be positive. Now let's think about this one here. I'm rotating counterclockwise, but I'm slowing down. Well, because at first I'm rotating counterclockwise, right? So I'm going in a positive direction, but I'm slowing down. So I'm losing positive values, essentially. I'm going towards negative values. So my change is negative. So my change in velocity is negative. So this is going to be negative. And then I can rotate clockwise. Let's think about the last one. Rotating clockwise. So I'm speeding up. I'm speeding up in the negative direction. The change in velocity is negative. So think about the change in velocity, all right? Think about the change in the velocity when thinking about the direction sorry, we think about the sign to put in front of acceleration. Think about what direction is the change. Is the change getting more negative? Is the change getting less negative? If it's getting more negative, then alpha is going to be negative, and if it's getting less negative, then alpha is going to be positive. All right. Or if I'm going positive in the positive direction, alpha will be positive. If I'm going positive in the negative direction, alpha will be negative. So yeah, how that works. And lastly, tangential acceleration. All right. An object experiencing an angular acceleration will still experience, I think we've seen before, centripetal acceleration, and we've seen AC, right? As well as a tangential acceleration. So if you remember this diagram from the beginning of the video, remember we have an angular velocity and we also have a tangential velocity. Now, so the main difference between this, so the main difference between what's going on here and uniform circular motion is that here we are accelerating tangentially as well. So because we're moving faster, because we're moving faster, our linear velocity is also going to get faster. So our tangential acceleration is referred to as AT, right? I'm sorry, anyway. So because this is changing over time, right, I can divide this by time, and this is going to be my AT. It's going to be my alpha, right? So let me just wrap them quickly and then have my drawing nicely. So alpha AT, right? My tangential acceleration will always point in the direction of linear velocity. All right, always. It's not the same as angular acceleration, and just so you know, we still have the centripetal acceleration. Don't confuse it with the angular acceleration. The centripetal acceleration comes from it rotating, and it's a force vector that points towards the center of the of the circle that we're forming when we move around. And the tangential acceleration here in this case, we are moving in non-uniform circular motion. All right, we are moving in non-uniform circular motion. So because we're doing that, we have a tangential acceleration. This one points in the same direction as the linear velocity, and we also have an angular acceleration. Right, this is just how fast the wheel is rotating. Those three different things, and they're still all present. All right. So here I say, what's the difference between uniform circular motion and non-uniform circular motion? Well, non-uniform circular motion experiences tangential acceleration. All right, non-uniform motion experiences tangential acceleration. All right, and yeah, just the last thing we have here. Like I told you earlier, kinematic equations and the rotational for linear motion are very similar to that of rotational motion. So if I want to get a position in rotational motion, it's theta, and it's units of radians. My velocity is going to be v over delta theta. It's going to be my angular displacement over time taken, and it's going to be in radians per second. My acceleration is going to be angular acceleration, and rather, sorry, let me call these the right things. This is omega, and angular acceleration is alpha. It's going to be delta omega over delta t, and this is going to be radians per second squared. Constant velocity equation with no acceleration really is the same thing for us, for theta I plus at, right? And then these two equations right here are, we have theta f, my mistake. We're going to have omega f, because that's velocity, right? And we equal to the initial angular velocity plus alpha plus t. Then here we're going to have theta f is equal to theta I plus, so this one here is the constant angular acceleration, and these two I'm writing here. So this is apologies, this equation has a mistake. This here is constant angular velocity. That's the equation for constant angular velocity. And then these two here, you use them when you are moving with an acceleration. So this is going to be theta I omega I, the initial angular velocity, times time plus 1 over alpha t squared. All right. So I hope this video is useful. Just to summarize, we'll be dealing with rigid bodies instead of particles. So we're going to consider how the shape affects the dynamics of our equations, which is frankly amazing. Angular acceleration points in the same direction as velocity when speeding up, as linear velocity, and opposite when pointing down and slowing down. Tangential acceleration points in the same direction as velocity. All right, and the equations are very similar to kinematics. I know I haven't gone through graphs, but we'll go through that in class. The AT, VT, XT graphs, so that's work the same way as theta, omega t, alpha t. So I don't need to spend too much time reviewing them in this video. And I hope you enjoyed it, guys. Yeah, see you guys. Bye.